There are two main topics in calculus. The first is asking what is the rate of change? How fast is a function changing? This is the main focus of our class 2250. The other main question in calculus is what amount of cumulative change has occurred? And this will be more the focus of 2260. So let's focus on the first of these, the topic for our class, the rate of change. And the question is, given a function f of x and an x value, determine how fast the value of that function is changing at that given x value. Or another way to say this is, okay, if I change x a little bit, how much does that change y? Because if I know how fast the little bit of x change happens, then I know how much the change in y happens. And maybe I'll give you a little clue here. The change in y divided by the change in x. How much, if I change x a little bit, does that change y comparatively? A couple examples. You can imagine pouring water into a barrel at a certain speed. And the question is, how fast is the depth in the barrel changing? Well, that's asking how fast is the depth changing. The depth is a function, and I want to know how fast it's increasing. Or maybe I want to drop an object from the top of a building and ask, how fast is it falling after 3 seconds? And so again, I'm asking, how fast is it falling? I'm asking, how fast is its height changing? How fast is the height changing? What is the rate of change of the height? Galileo was one of the first people to investigate this question in a rigorous mathematical manner. And what he did was he went to the Leaning Tower of Pisa, and he had his assistant drop things from the top of the Leaning Tower and time them to figure out how far they had fallen in a given amount of time. So just by gauging how the angle and how fast it had changed, you could figure out that after 1 second, it had fallen like 16 feet. And after 2 seconds, how far it had fallen. After 3 seconds, how far it had fallen. And what he noticed is that the distance that had fallen was exactly proportional to the square of the amount of time it had been falling. So if it had been falling for 1 second, it had fallen certain far. If it had fallen for 2 seconds, it had fallen 4 times as far, because 2 squared is 4. If after 3 seconds, it had fallen 9 times as far. And so he used that to get a pretty good idea of how to track how far something had fallen after a set number of seconds. He discovered that the height after t seconds could be given by 186 minus 16 t squared. This is because the Leaning Tower of Pisa is 186 feet tall, and it falls at something proportional, 16 times, the square of the amount of time that has elapsed. After 1 second, it had fallen 16 feet. After 2 seconds, it's fallen 64 feet. This graph shows how height changes with time. The object is falling directly downward, but the parabola is height is 186 minus 16 t squared. Let's focus on finding out how fast the height is changing after 1 second. In order to do this, we're going to consider the height at 1 second and also the height at 2 seconds. We can figure out how fast the graph is changing on this interval by simply taking the change in y and dividing it by the change in x. We can get a more accurate estimate by using a smaller interval of time. Instead of going from 1 to 2, we can go from 1 to 1.5. And notice that this line lies closer to the black curve, which is the height. Our estimate can be improved farther by taking an interval of 1/10 of a second. And again, zooming in, you can see that that blue line hugs closer to the actual curve in black than the red or green lines. We can extend this process mathematically by, instead of taking it over 1 second or a half a second or a tenth of a second, as to take it instantaneously at 1 point. And again, we can see that this line hugs the curve even closer. So in the example we just worked, we were considering how much y changes relative to x over a short period of time. So that is going to be y2 minus y1 over x2 minus x1. And of course, by now we've recognized that this is in fact just the slope of the line. So we've noticed that we started by taking smaller and smaller intervals. We got these numbers closer and closer together. So the question is, if I change x just a little bit, how much does that change y? So what we're going to do is we're going to take the secant line that connects 2 points, and we're going to find its slope. But then we're going to make the points get closer and closer together. And so by using something that's called a limit, which is going to be the discussion for the rest of this chapter, we're going to go on to figure out what is the slope of the tangent line, which is where essentially I'll put basically x2 is going to equal x1. Well, obviously, if x2 equals x1, I'm dividing by 0. That's a problem. That's why I'm going to need this idea of what a limit is. But the idea is that basically we're going to connect 2 points together, and we're going to connect 2 points that are closer together, and we're going to connect 2 points, and eventually we're going to end up connecting the point with the exact same point on top of itself, and you're going to get the slope of the line that hits the graph at just that 1 point. And that will be the idea of what is called the tangent line slope, or what is sometimes called the instantaneous rate of change. Instantaneous meaning it's happening at 1 point. Often with the secant line, we'll refer to what is called the average rate of change. But in order to get from this average rate of change, this instantaneous rate of change, we're going to discuss the idea of limits. And that is going to be the focus of the rest of chapter 2. I wanted to quickly show how I computed those slopes. So I took the function value, which is 186 minus 16t squared. That's what Galileo figured out, because the Leaning Tower of Pisa is 186 feet tall, and then its height changes with the square of the amount of time that's gone by. So I took the numbers 2 and 1 and plugged them into here. That's 186 minus 16 times 4, minus 64, minus, I plugged 1 into here, 186 minus 16, divided by 2 minus 1. So this is going to be a slope, negative 48. I did the same thing with 1.5, got negative 40. Did the same thing with 1.1, got negative 33.6. And the idea is ultimately that, okay, here I took a step of size 1, a half size step, a 10 size step. Well, it is, okay, if my step is h big, and that's just the letter mathematicians like to use, the letter h. If I take a step that's h big, what kind of slope am I going to get? So I'm going to plug 1 plus h into here. So that's going to be 186 minus 16 times 1 plus h squared, minus 106 minus 16. And then, of course, 1 plus h minus 1 is h. And the idea is, as h gets really, really small, as h gets close to 0, well, notice that the top is going to get close to 0, and the bottom is going to get close to 0. But the idea is that we're going to use those limits, which is the study of the rest of this chapter. We're going to use limits to figure out what happens as h gets really, really close to 0. And what I've worked with through all of these things is something called the difference quotient, which is f of x plus a little bit, h, minus f of x divided by h. The difference quotient will be very useful in chapter 3. But first, we have to turn our attention to chapter 2, where we talk about limits and how to deal with things like this. Well, have a marvelous day, and I'll see you in class.